Hi friends, let's continue our derivation for the Michaelis Menton equation. If you remember, in our last video we discussed about the equilibrium approach, which was the very first approach that was used by Michaelis and Menton to work on the enzyme kinetics. This approach was slightly modified, but which brought a great revolution in this enzymology, and which was a more what you call as an applicative kind of approach, which is popularly called as the steady state approach. Remember, so there are two kinds of derivations we have. One is the Michaelis Menton equation derivation by equilibrium approach, which was the original approach used by Michaelis and Menton, and the second one is the steady state approach that was given by the Briggs Haldane. So it is given as the Briggs Haldane modification of the Michaelis Menton equation. So if you start with the initial reaction where we consider a single substrate, single step enzyme catalyzed reaction where your E plus S combines to form ES, which further forms E plus P. This we say that K1 is constant as K-1, this is K2, K-2. So if you remember earlier, the equilibrium approach told that this entire can be neglected because there is an equilibrium established as soon as E and S combine to form ES. And therefore, the breakdown of ES to E plus P was totally neglected. But now we know that this particular thing does not actually happen. Most of the enzymes, they work at a very high pace, at a very fast rate, wherein your ES gets converted to E plus P very quickly, which will disturb this equilibrium. But with time, it is found that the concentration of ES, it remains constant. So remember this, the steady state approach says that the concentration of ES, it remains constant. Now it remains constant, right? Because the rate of its formation, so let us go for this. So rate of formation of ES, right, is exactly balanced by the rate of breakdown. So the rate at which it is formed, it is immediately balanced by the rate of its breakdown. So these two rates are exactly balanced as per the steady state approach, which is the actual fact. So here the rate of formation of ES, you can see ES is being formed from E and S. So you can say that K1 into E into S, right? This will form your ES is equal to rate of breakdown. Now in the equilibrium approach, ES we consider to be broken down only into E and S. Here we consider that ES can be broken down either into E and S or equally into E plus P. So here I will say this is either your K2 into ES or plus your what you call as your breakdown we are talking about K-1 into your ES. Right, here I have not considered the formation of ES from E plus P because we neglect this, only this. In the steady state approach, though we are in the initial period when we say, so here the concentration of product is very less. So we consider ES being formed, ES being broken down to form E plus P, but this product is still less in the initial period. Therefore, product combining with the enzyme to again form ES is very less. So we have neglected this. So here we have K1 into E into S is equal to K2 into ES plus K-1 into ES. So now taking your ES common there, so you have ES into bracket K2 plus K-1, right? So here you have your, again taking constants to one side, you have E into S upon ES. This is equal to K2 plus K-1 whole upon K1. Now this K2 plus K-1 whole upon K1, this we represent as what is called as your Km, that is your Michaelis Menton constant. So we represent this as Km. So if you write the equation now, it is like E into S whole upon ES, which is given by Km, right? Now again come back to the total enzyme which we saw earlier. So total enzyme is the sum of your free enzyme. So you have a total enzyme. This is equal to your free enzyme, that is E, plus your bound enzyme, that is ES, right? So आपके पास जितनी total enzyme है, some is still free and some of the enzyme has bound to your ES complex. From this, if you calculate the value of E, you have E0 minus your ES, right? Now similarly, as we substituted the value of E, now further derivations are going to be similar. I will substitute this value here. So now I have in my equation, oh not here, in this particular equation here we will substitute it. So here we have E0, right? So it is your E0 minus your ES, right? Be with me, into your S whole upon your ES, which is given by your Km. Right? Now I take this ES there, open the bracket. So here, if you see, we have your E0 multiplied by your S, this minus your ES into S. Now this, as I told, I will take this side, so it is Km into your ES. Now taking ES to one side, I have this is equal to Km into bracket your ES. This, when it goes there, it will be positive, so it is ES into S. So I take ES common from this. So when I take ES common, I have ES into bracket Km plus S. Okay. So now I take the value of ES from this. So यहाँ से आप ले लो ES is equal to, this will go down. So here I have my E0. So E0 into your S whole upon your Km plus S. Right. So I hope you are with me. So far, so good. So we have the value of your ES. Now we know that ES is the term which determines the velocity. If you come back here, ES is being converted to E plus P and the constant here is K2. So if I am talking about the velocity now of the reaction, okay, let me choose. Okay, so you have velocity, that is V0. So V0 will be given by your K2 into ES. So ES की value इसमें substitute करो आप. So what will you get is your V0 is equal to your K2 into your E0, right? I hope you all are with me, into S whole upon Km plus your S. Right. So far, so good. Now total enzyme is involved. So when you have say 100 molecules and all enzymes are working within full-fledged, so you have reached the Vmax, the maximum velocity. Do I have one more? Yes, I have. So you have your Vmax. So I will represent this as Vmax. So Vmax is equal to, as I know, K2 into my E0. Right? So this is my Vmax. So here I will substitute my Vmax. So my final equation would be V0 is equal to my Vmax, right, into your S whole upon your Km plus S. So if you compare this with your earlier equilibrium approach, you will find this is similar, only difference is that here you have Km. In the earlier equation, here we had Ks. So with this, we end our steady state approach, a more what you call as applicative approach, because here we have taken into account this K2. Remember, the Michaelis Menton assumption may be applicable in a cases where the value of K2 is very, very less. That time, there is an equilibrium between two. So you can say Michaelis Menton approach is a special case of a Briggs Haldane approach, which is a wider approach encompassing most of the enzymes. So stay tuned with me, Professor I Kukreja, for more such equations, derivations, microbiology and enzymology. Thank you.